It's our pleasure in episode 7 of season 2 to talk about a subject that shouldn't be controversial, but it is a little bit misunderstood, and that is how does air abrasion affect a restoration? Again, in the 6 lessons approach, we have an analysis of the bottom part of the restoration and the top part of the restoration. The middle has connections, so we're connected bottom to top, and it's a bottom to top restorative process. So there's 2 times when we in our protocols use air abrasion, and we do them with specific purposes based on specific science. The first is creation of the hybrid layer. Now, when we talk in 6 lessons about the creation of the hybrid layer, we're trying to set a particular foundation that you understand that a hybrid layer, which is our logo, we have 4 layers in our logo because there are 4 zones in the hybrid layer using a mild self-etching bonding system. Now, understanding that phrase, a mild self-etching bonding system, that has been developed and published for decades now. But interestingly enough, the idea of a self-etching bonding system was an unintended consequence. Now, in science, there are usually surprises, and hopefully the surprises don't have catastrophic. My favorite movie of the last year was Oppenheimer, because right before they exploded the first atomic bomb, General Groves, who's supervising for the government the project, came to realize that there was a slight possibility that once you started a chain reaction, everything would become part of the chain reaction and you'd have a destruction of the known world that we have. That was just a minor piece of science thrown out by one of the researchers at Los Alamos, and General Groves was like, how close, to zero is that? And Oppenheimer said something like, well, it's very close. It's like, but it's not zero. Okay. So in science, when you do things, it's not like everything is always understood. And when we developed adhesive dentistry, or the adhesive dentistry principles were being developed, it had to become understood little by little by little. And it starts in 1951 when a chemist from Switzerland who really didn't know anything about dentistry came to market with a product that bonded to dentin. That was the claim. 1951, Sevraton. Oscar Hager made the claim. They sold it to dentists. Only one problem. It didn't work. False advertising? Perhaps. But in reality, he had some tests where on flat dentin surfaces, this Sevraton polymerized and it stuck to the dentin. And so that was the first step. And then they decided to put a white plastic material called polymethyl methacrylate on top of that, which had a shrinkage of about 8%. And so if you put it in a tooth and you had that much shrinkage, all of a sudden you get no bond in the first hour, and it was a terrible disaster. But what can you say? That's history. Well, that product, GPDM, was the monomer, had a polymerizable monomer that was very good, polymerized with a chemical cure reaction. And then when the revitalization of adhesive dentistry came after the Japanese products became successful in the early 80s. This was 30 years after the Sevraton disaster. Kerr, a large manufacturer of dental products, hired a young chemist named Al Kobashigawa. And Al Kobashigawa had a master's degree from Cal State, LA, very bright chemist. And he was given the task to create a bonding system for Kerr that could compete successfully with the Urabe and also the Alleman products that were coming out of Bisco. Those were the 2 leaders. Anyway, so Al, he didn't know anything about dentistry. He knew about chemistry, but he knew that patents were kind of important because they protected some proprietary information. And the proprietary information, when you did a patent search on dental adhesives, came up with this patent application 1951, 1950 by Oscar Hager. And he saw this molecule, GPDM. And this glyceryl phosphate dimethacrylate, Al speaks chemistry and he knew that he could make it. And he started to experiment with it. And then he started to talk to some of the people in Japan. And the people in Japan at Urabe are great chemists. Most of them have PhDs. But, if you have a master's degree in chemistry, you can talk the language. Plus, Al was Japanese. So Al Kobashigawa, speaking probably in English, not Japanese, with other researchers, found out that the original GPDM molecule that polymerized and bonded to dentin, when the Japanese made the molecule to try to reverse engineer this bondable product to dentin, that Hager claimed bonded to dentin, but when the Japanese synthesized the molecule and polymerized it on top of dentin, it didn't bond to dentin. So what do you say? You say, well, they were just lying or whatever. I mean, but they figured that there was something happening that they didn't understand. And they turned out that they were able to, I think, maybe get some inside information. I mean, it's, this is 1970s, 1950s, 20 years later, but chemists talking to chemists found out that the synthesis of the GPDM by the British and Swiss chemists had a contamination of nitric acid in the synthesis. The Japanese, when they synthesized it, did not have the contamination of nitric acid. So what that meant is that there was an acidic part of this early bonding system that actually changed the dentin and allowed the GPDM molecule to adhere to it. But when the Japanese did it, their purification was so good of the GPDM molecule that without the nitric acid, it did not bond. Now, this is history that nobody knows, nobody talks about, hasn't been written about. It's all proprietary information, company against company. Al's a good guy. And the product that they came up with took this molecule from Oscar Hager in 1951 and the technique of taking away the smear layer that Fusiyama innovated in 1978, which was acid etching with phosphoric acid. And he got that idea from Bonacors using modification of phosphoric acid on enamel to allow this Severton molecule to polymerize to enamel, and it did. But without the phosphoric acid etching, Bonacor could not make the adhesion happen with this product. I mean, this is, you go in 1950s, and then you go 1970s. They've got different approaches, different molecules. The first bonding molecule that Urabe put to market was called phenyl P. It was quite acidic, but again, that acidic molecule, phenyl P, was put in to polymerize in a moist environment. So you needed to have an acidic end and a polymerizable end, which is the methacrylate end, hydrophobic and hydrophilic, and that was the way to mix and get integrated before the polymerization into this moist dentin substrate. Oh my goodness. Well, the bond strengths with acid etching increased dramatically because the smear layer was removed. But the bond strengths were still in the 10 megapascal range instead of the 4 to 6. Well, that's a big deal. But that's still not anywhere close to the connectivity of a tooth to itself. So if you have a bond that's in the 5 and 6 range and it's bonded, but the actual tooth is connected at 10 times that strength, it's not like a tooth. It's not like life. It's not biomimetic. When the progress started to be seriously undertaken by Urabe in conjunction with TMDU, the innovation of phosphoric acid was accepted. All of the products in the 70s had this conditioning step. So the removal of the smear layer by phosphoric acid, that's called conditioning. If you didn't condition by removing the smear layer, then your bond strengths would be 4 to 6 rather than 10 to 12. But they were still seeking for higher bond strengths. And polymerizable molecules are not easily made, but chemists at Urabe came up. Umura is the famous chemist who is totally unknown because they kept his name secret. Why? I don't know. But Umura, working for Urabe, came up with the molecule 10-MDP, which is a much longer molecule than the phenyl P, longer also than GPDM. Now, the length or size of the molecule becomes important because of what's called stoichiochemistry. In other words, sometimes molecules don't fit because they're too wide. So skinny molecules sometimes have a big advantage if they're snaking into small areas. And this 10-MDP was like that, long, skinny, 10 carbons on its chain that separated the methacrylate end from the phosphoric acid end, the hydrophilic end, which is phosphoric acid, and the hydrophobic end, which is the methacrylate. Anyway, so Umura comes up with this new molecule. They start testing it, and it's twice as good as phenyl P. But because they have this experience with phenyl P, they're a little loyal to it. Their first projects, when they use the 10-MDP, then they made another project. They say, well, maybe these smaller molecules work better as they're integrating into parts. It was a good idea. And so they made products that have half phenyl P and half 10-MDP. And this product that came out was the game changer. And that combination of phenyl P and 10-MDP in the primer and in the adhesive was called Liner Bond 2. And Liner Bond 1 had 10-MDP in a dental bonding system, but it was a dual cure with a very thin adhesive layer. And it was a 2-bottle, 1-bottle system called Photobond. The thinness of the adhesive layer is a problem. If it's too thin, it doesn't polymerize because of air inhibition. And transudation coming from underneath thins out that adhesive layer. And Photobond had this problem. It was a great bond to enamel. And when Liner Bond 1 came out, it was touted as both a dentin and an enamel bond, but it had 5 steps. It had a conditioning step with an acid that was a little less aggressive than phosphoric acid. That's a good idea. And that was called calcium citrate, or a Ca conditioning solution. But then to overcome the problem of removing too much hydroxyapatite, which caused the collapse of the collagen if it was dried, then they had a primer. So you got the conditioner acid, weaker acid, and then they had a primer, which is called SA primer, which helped fluff up the collagen and separate the collagen fibrils so they could be infiltrated by this photobond. But the photobond, again, was too thin in an adhesive layer, and so that didn't work well on dentin because we had transudation, air inhibition. You put the light on it, you still had problems, sensitivity. And then they came up with a very important product in that liner bond system, which was called Protect Liner F, which was the first flowable composite in the world. And so the liner bond system comes out in 1989 in Japan, 1992 in the United States. And it worked on both enamel and dentin, but it had these 5 steps. And so it's a little complicated. And my first mentor, Ray Berlotti, took it upon himself to simplify that and not use SA primer. And then he used the bond flowable composite that his company had made, which wasn't as good as the flowable composite that Urabe made. And there was just a lot of confusion. He also used phosphoric acid again because he thought that it was pretty cool that you could make your own phosphoric acid and make it for cheap rather than expensive phosphoric acid that would come from other manufacturers. I mean, Ray Berlotti had a vested interest. He owned the company Danville. But all of this confusion that when I'm first learning adhesive dentistry is confusing. And if you're listening to this podcast and you're going to listen to it again and listen to it again and write it down, hey, feel free. I'm trying to make your life easier. Now, in reality, are you ever going to need to know or use liner bond 1? No. How about liner bond 2? No. But liner bond 2 that exclusively eliminated the removal of hydroxyapatite had that because in experimentation, when they're transitioning from the liner bond systems to this liner bond 2 or the liner bond 1 system and the Clearfield F1 and F2 systems, they did an experiment. And the control was, we get this bond strength of about 25 megapascals with acid etching. Well, let's see if we had no acid etching. They did understand that the 10-MDP molecule had an acidic effect, and so they tried it without acid etching, just using the mild acidic effect of the 10-MDP molecules, and they found out they actually had higher bond strengths without phosphoric acid. So when they're coming out with this new liner bond 2 system, it's like, they eliminate the acidic conditioning. Wow, it's a big step. Got to make up a story, and the story is the monomers are integrating in with the smear layer, so it doesn't need conditioning because of this magic monomer. And the bond strengths that they get onto dentin are in the high 20s, low 30s. Sometimes a little bit higher. Actually, there's one test they had 42, I believe. But it showed that modifying the recipe of your bonding system modifies the strength, which is related to how the hybrid layer is formed. Okay, so then this kind of becomes the gold standard. And then a couple of years later, SE bond, which eliminated totally the phenyl P, that was the step forward that brought that into now the 40s. So with the liner bond system that's getting the 30s, now you eliminate phenyl P, only use 10 MDP, and you don't have a conditioning step with acid. Now they're getting 40s and above. So SE bond becomes the gold standard. For the 20 years that it was under patent, it was the gold standard. And that patent on the MDP molecule, 10 MDP molecule, kept the competition away for almost 2 decades. But then as soon as the patent expired, other products that use 10 MDP, because it's known in the science that it's the superior molecule to any others, as it goes out, it starts to get tested. So this is 1998, 1999, 2000, 2001, 2, and then 2003, Bart van Meerbeek, who is the premier tester, for 10 years, he's been at Catholic University Leuven, Belgium. He compares Optibon FL, which is now the gold standard with the GPDM and the phosphoric acid conditioning, a 3-step total etch technique. And then he compares it with this up-and-coming gold standard, SE bond, and he varies the conditioning steps. So with no conditioning, which is the Urabe recommendation, it was an innovation, a breakthrough in 1993. Liner bond 2 came in 1993, in the United States in 1996. But in 2003, Van Meerbeek tries it with the manufacturer's recommendation, and he gets a bond strength of 36, and that's about what everybody else was getting, which for the time when Liner bond 2 was created, it was a huge breakthrough. But again, it had this mixture of phenyl P and 10 MDP. So when they eliminated it, now we're getting higher bond strength. We're going into 37 instead of 27. But then Van Meerbeek has the good idea of using a technology that was introduced in the mid 80s and investigated by a very important investigator in London named Alan Boyd. And this was abrasion. In the United States, abrasion had been used early on by SS White Company to prepare preparations that didn't really, if the preparation had any size, it really wasn't a good idea. But the idea of drillless preparation, Dr. Black from Texas had this innovation, and it was used, developed. Now it's still used in minimally invasive dentistry. Tim Rainey is kind of the father of that. But when Van Meerbeek used the abrasion to test bond strengths, he found out that just like Alan Boyd had said in 1985, when you air abrade, or he called it air polishing, you are removing most of the smear layer, which is just your chopped up dentin from your preparation with your burrs. And the smear layer interfered with the infiltration of early bonding systems in the 80s, still did the same thing when it's being tested 20 years later. But the interesting thing now is that the evolution of the dental bonding system now shows that you can go from 37 megapascals to 56 megapascals. But you have to use that conditioning step of air abrasion. It also has the advantage of stopping any fluid coming out of dental tubules by putting the smear layer that's on top of the orifice of the dental tubule and plugging it. It compacts it into the tubule. So you have a dry bonding field, but all of the intertubular dentin is exposed and receives the primer much better, maybe 30% better, and a higher development of the hybrid layer. And you get to these numbers that are 56, where now we're talking turkey, because 56 is greater than the connection of enamel to dentin. 2000, the connection of the enamel to dentin was established by Urabe and the team out of TMDU. Sano was part of that project. Tagami is part of that investigation, Nakajima, all stars telling us enamel to dentin, 50 megapascals. And now, if you use this gold center bonding system, but now in a better way by conditioning, meaning removing the smear layer in the critical areas and keeping the smear layer in the other critical areas that can help keep the bonding field dry so the primers aren't as diluted, then all of a sudden you got these numbers 56. Wow. And so you would think when that revelation came out that everybody at the Urabe company would be like buying stock in abrasion companies. If you understand a biomimetic approach, the advantages of a self-etching system are maximized when abrasion is used. And so it's something that we've always used. All of our long-term successes, 20, now going into the third decade of service, are all based on abrasion technology to condition the dentin. That means remove the smear layer intertubularly and compact the smear layer, the smear plugs that are in the tubes. All right, so that's abrasion for the bottom. Now, how about abrasion for the top? Connecting the enamel replacement to the dentin replacement. The dentin replacement, we call that the biobase. It's composites, direct composite placement. If you don't use abrasion, the numbers that you will get are around 25 megapascals. Now, 25 megapascals is not nothing. You will not have many debonds of your enamel connection to your dentin if you use only polishing with pumice rather than abrasion. But, I am a sick man. I'm trying for perfection. I'm trying to make no failures. That would make me the happiest. And the closer we get to no failures, the better. But if you have a debond of your enamel replacement to your dentin because your bond is 25 megapascals, it just means that it wasn't strong enough to resist the fatiguing of chewing, a million times a year. And occasionally a natural tooth will have a fracture of the dentin off of the enamel off of the dentin. Okay, so that's kind of biomimetic. But when these numbers are lower and I'm looking at them, I'm going, well, we got this research team in Denmark that just showed if you used abrasion that you could get those into the 30s very easily. This is an early paper published like 1998, 2000. Putsfield, that's a nice name, huh? And Asmussen showed that. And Putsfield and Asmussen, said, yeah, you just use abrasion and all of a sudden you're accessing more of the unpolymerized monomers that are in this direct composite. So their idea was how to make a composite repair. But I'm taking these ideas from the composite repair techniques into the cementation of our enamel replacement into the biobase. And so the idea is that in composite, when you put the light on it, the polymerization is going to be about 65% of the monomers are going to now be into polymers. But there's little islands of monomers that never get reacted through a free radical connection. Those are still accessible, but if you have a flat surface and you do abrasion, all of a sudden you're doubling the surface area. So you're increasing the accessibility to the monomers. And that's why the difference between 35 with no abrasion and 56 with abrasion, that is like you also in that hybrid layer were accessing and not only removing the smear layer, but you're actually accessing or making a better surface area of the intertubular dentin. And so you have more access to hydroxyapatite. Same thing on your biobase. You're having more access to the uncured monomers, and those through a diffusion reaction, once the heated composite and the uncured adhesive that wets the surface after abrasion, and then the heated composite and then the uncured adhesive on the intaglio surface of your onlay, once they're squished together at about 200 microns thickness, you put the light on it and there's a diffusion. The reaction of the heated composite is going two directions. It's diffusing into the surface area that's been increased on your biobase, and it's diffusing into the intaglio surface of your enamel replacement. And all of those are polymerized at the same time in your final cementation light cure step. And so then you get about 40 megapascals. And so that number was established in the 2012, something like that. And so we now have a onlay that has a cohesive strength in the 40s. We have the layer of the cementation that's in the 40s. We have the dentin replacement in the 40s. There's no weak link there. The only place that we really have a weak link that's not in that 30 to 50 megapascal range is at the resin coating level, where we use stress reduce with Ribon to protect the developing hybrid layer on areas where there is residual decay that has been left after killing the bacteria in that residual decay. And that allows us to have a hybrid layer without taking the risk of exposing the pulp. And that's been our protocol, our strategy. And, millions of restorations are around the world doing this. And this is the approach that the 6 lessons takes. So air abrasion for highest bonds in the hybrid layer, air abrasion for the highest bonds in the connection of enamel to the dentin. And if we did have over the years some type of traumatic force or occlusal forces accumulating, then we have a built-in safe strategy or a fail-safe strategy, what we call a secure bond strategy, using that in the first millimeter of dentin replacement in our central stop zone around the pulp, a fiber placement to protect that in the case that we ever did have a failure of the dentin replacement. It's only happened once. We have a case of that in the PowerPoint when we train doctors. Worked very well, but it's only happened once in 20 years where we've had a fracture of the enamel, go to the fracture of the dentin, and stop at the central stop zone with the Ribon placement. So if it never happens, that's even better. We want all your teeth to not break. Unfortunately, some teeth without any decay, without any restoration, still under the years of occlusal forces, have some failures. So here we are. We're in an imperfect world, but we're trying to make it as good as possible. So with that, we'll just sign off till our next lecture on 6th Lesson podcasts. Get bonded, stay bonded.